So I handed back your quizzes and homework. Um, Thank you for making grading so much easier this week. I handed out tens like they were candy on Halloween. Like, awesome work. I feel really good about the fact that I said this is like what statics is, this is what you need to be able to do when you leave, and then you all nailed the quiz, did well on the homework. Like, good work. There's hope for you yet.
There was no 3D vector stuff with this section, so it was a lot, I guess, easier
Okay.
in terms of calculating.
Yeah, good. So, good work. Yeah, that's going to be half of our midterm, right? The next midterm is going to be doing that, so should feel pretty happy. How many frames and machines problems did you do since Wednesday? 2! Nice! All right, I asked for 3, but 66% is a D, so there's that. Okay, keep doing them because that's going to be another chunk of the midterm, right, is doing frames and machines. So I haven't given you your graded problem yet because I was hoping that by not distracting you with the graded problem, you might actually just do some for the sake of doing some, but at this point I'm going to have to post the graded problem and hope you just do some over the weekend on Monday, maybe? Okay?
Always do homework on days off.
All right.
Monday off next week. That's really nice.
Yeah, we do have Monday off next week, so. But today we're starting chapter 7, okay? So let's dive into chapter 7. And chapter 7 is all about internal loads. Okay? So this is going to be really key for moving along when we get to strength and materials, which is not winter term but spring term. And so far we haven't been looking at all about whether a member can.
You mean it is winter term?
Yeah, it is winter term.
It's next term.
I'm enrolled in it.
Yeah, it used to be spring term. Sorry about that. Strength and materials is next term. Dynamics did a little switcheroo. It's been a year. You'd think I'd remember, but I don't. So, sorry. This is next term, right? We're going to be doing the how things break, essentially. So far we've been saying when we draw a truss and we figure out that it has 900 million pounds of tension force on it, that's no problem, right? Well, at some point it could be a problem if we use something too small to hold 9 million pounds. But in order to actually design parts, we need to be able to quantify the forces that they're going to carry from a design perspective, okay? And it turns out that we use method of sections to do that. So we're actually going to go back to our classic beams. This is the classic levitating beam, right? Little gap there, it just hangs out, okay? And maybe we have something on it, some distributed load over the first half of it, and then maybe a point load right here. And we need to figure out, will the beam break or not? Okay, well, we probably need some numbers on the problem to do that, but so far all we're able to do right now is to figure out what the reactions are at A, right? AX and AY and maybe BY. But we don't really talk at all about whether this 2x4 is going to carry the million pounds that we put on it. All right? And it turns out that the loads in this 2x4 change as you go along its length. Could you believe that? Does it look like that happens, right? Okay. So we need to develop a system for quantifying the forces that are inside of this beam. And that's what chapter 7 is all about, is developing that system. The reason it follows chapter 6 is because the way we do that is by taking the method of sections. So if I slice this guy along, maybe I'll put some little plane here, AA, okay? Then if this were a truss, what would we do? if we were analyzing this?
The forces and the beam or something.
Yeah, Sierra's kind of going down the right track here. We'd draw a free body diagram of it still in static equilibrium, right? With the loads still applied. Like this. And then we'd put some stuff where the cut is, right? And so far, we've been saying in trusses we are dealing entirely with two force members. And so we'd say that there's just a force coming out here. And in fact, that's what we're going to keep doing. But that doesn't, would that keep this in static equilibrium, just having one force coming straight out of that cut face? No, why not, Brendan?
Because the force is going to be in the y direction, and that
Okay.
force is only in the x direction, the way you drew it.
Right. So this force is only in the x direction, and Brendan's astutely saying, hey, there's up and down forces. Okay. So maybe there's going to be some force. Let's draw it this way. Okay. All right. And it turns out you can't see it intuitively, but there's actually a third couple moment that we're going to put on here. Okay, and it's the bending moment. So this first force that's horizontal in the x direction, we're going to call that our normal force. We just denote it with an N, and it's always normal to the cut face. So I've cut this, it points straight out from the face. The vertical force, I'm going to give V. I don't know why it's a V, because it's the shear force. So I don't know why V.
Very sheared.
Vertical, very sheared. I don't know. I don't know very many V words. But that's what it is. We use V for shear in this class. Okay? So these are the three forces that we're going to have to quantify. The bending moment, the normal force, and the shear force. Okay? And we always draw them how I have here. Now, if we looked at the other side of this, right, remember when we did method of sections, we could either look at the left-hand cut of the cut or we could look at the right hand of the cut. Let me draw the right hand of the cut now. So my free body diagram would be something like this. And then, in order for this to be in equilibrium, the forces at the cut face have to be equal and opposite from how I drew them on the other side. Normal still comes out of the cut and is horizontal. Shear has to be equal and opposite to this V, so that means it has to be up. And the moment has to be equal and opposite to this moment, so that means it curls this way. All right? Now I've still drawn all of these with their positive sense. But you say, wait a second, Andy, you've told me that counterclockwise is positive for a moment, and over here you've drawn a moment that's clockwise and you're calling that positive. Yeah, I am. Okay? So this isn't the same thing as the sign convention of when we actually say, hey, let's sum the moments about the cut. That is where I say counterclockwise is positive, right? But that is different than saying which one of these causes a positive bending moment on the beam. Okay, so this is my sign convention for doing a summation of the moments. This is what I say if a beam has 100 Newton meters of positive bending moment on it. It's telling you the sense of how that beam bends. Okay, so let's talk about that sign convention. Let's do the normal force first. It's positive. Okay. It's positive when it's directed away from the cut face. So we always, whenever we cut, we draw it going out of that face. That's what we would call a positive normal force. It also is would be a tensile force. Right? So if there's a normal force pulling on this beam in this direction, that means it's a tensile force. It's stretching the beam instead of compressing it. Okay? The next one let's talk about is the shear force. Maybe I'll put that on here as V, the normal force is N. The shear force is positive when it causes a clockwise rotation of the beam it acts on. Okay. So what does this mean? If we look at the left-hand portion, V is pushing down, right? Which would cause the beam to spin in a clockwise motion, right? Over here, V is pointing up, which would also cause the beam to spin in a clockwise motion. Okay, so this is considered a positive shear force, one that causes a clockwise rotation of the beam. All right? Then the last one is what we call a bending moment. That we've denoted here as M. And it's positive when it causes a happy beam. And by that, I mean concave up. Right? Turn that frown upside down. Okay? Yes. Okay? So here's the eraser, right? If I grab this on the end and I induce a moment trying to twist it like that, it bends the eraser into a smile. That's a positive beam, right? If I twisted it the other way, right, if I start here and I twist that way, that's a sad beam, okay? So positive beam, that's I'm grabbing on this end, so right now I'm showing you what it would look like if we're looking at the left. I twist this way to make a happy beam, that's positive. Now let's look at the other end of the eraser. Now if I twist this way, positive, happy beam, right? If I twist it this way, sad beam, negative, okay? So positive bending moment causes happy beams. Everybody got that? Okay, cool. So with that in mind, let's take a look at the simplest of beams. Okay? I'm going to label some points here. A, B, C, D, and E. Can anybody tell me the reactions at A and E? Nope.
No.
Just the reactions. We're just solving for the reactions. Yeah, so what's AY and EY? Hmm? 5, right? Yeah, that's all I was looking for. I don't try and trick you that often, do I? 5 kilonewtons. Okay? All right. So let's section this beam at B. We've solved for the reactions. Always a good idea on any problem we're working on. So we solved for the reactions. Let's section this beam at B and figure out what the internal loading is at B. So to do that, we draw the chunk of the beam we're interested in. We put the loads that are acting on it. And then we draw our unknowns in the positive direction. So I'm going to have some unknown normal coming out, some shear going down, right, because we want it to spin it clockwise, and I'll have some moment making it a happy beam. Okay. How many unknowns do I have? 3. How many can I solve for, you think? Why?
Because you can do a moment, you can do a normal, or an X, you can do a Y.
Yeah, so I can sum the forces in X and Y, and I can sum the moments about a point, because it's not a particle, it's a rigid beam, so it has shape, so we can do moments, okay? So, let's sum the forces in the X direction and set them equal to 0, and I'm going to say right's positive, and it looks like I have normal is equal to 0, right? Nothing else has a component in the X. Let's try some of the forces in the Y. What do you see acting in the Y?
Shear force.
Okay, so 5 kilonewtons.
Shear force.
And the shear force, do I say plus the shear force or minus the shear force?
It's positive. Right?
But it's going against the,
Going down.
yeah.
It's
going
like
against
positive
the
when it
convention.
causes clockwise rotation on the beam. That's causing
Yeah, yeah, positive.
Because
you're subtracting
so clockwise.
There we go, Paul's got it. We're subtracting the positive shear force because the sign convention is if the arrow is pointing up, it's positive. So 5 is up, that's positive. V is down, so it's going to be negative V equals 0. Now, if I was saying, is the shear force positive or negative on this, if I get a positive value when I sign for this, or when I solve for this, and it's pointing down, it's positive shear. But when I'm doing a force summation and I say up is positive, shear is negative. Okay? So when we solve for this, it looks like the shear force is 5 kilonewtons. Okay? And then let's sum the moments. We always sum the moments about the cut face. Okay? So I'm going to say about C, and that equals 0. I do mean B. Now, well, no, I mean C for cut face.
Oh.
But, so I'll say cut. Okay? So what are the moments about the cut?
Negative V times 2.5.
Oops,
So
but
that'd be negative 5.
but the cut's right here, right?
Oh.
So V actually acts on the face of the cut.
So we need to do the 5.
Yeah. So it'd be negative 5 times 2.5, assuming this is in the middle. Anything else cause a moment? There's something labeled moment. M, right? So we've got this M that we drew in the positive direction, so I'll say plus M equals 0. So it looks like the bending moment at C is going to be 5 times 2.5, which is 12.5 kilonewton meters. Okay. Now I'd like us to move to C, but we're going to move just to the left of C. So do you remember when you're doing limits in calculus and you have like an asymptote and you'd say like go to 0 but the plus side of 0? Everybody remember that? A little bit? We're looking at C, but not exactly at C where this 10 kilonewtons applied, but just an infinitesimal point to the left. Okay? So let's draw, let's go to, I'll call that C minus maybe, right? Because we're just not quite to C. So let's draw our free body diagram for this guy. Okay. Somebody help me with what I need to do on the cut face. Jordan?
Draw it all versus the normal, the shear and
Okay, which way do I draw the normal?
out.
Out. Okay, normal's always out. Which way do I draw the shear?
Down.
Okay, but that's not always the rule. What's the rule for how I decide how I draw the shear?
Clockwise rotation.
Yeah, so in this case, you're right, it's down, but I just want to emphasize it's not always down, right? It's in the way that causes clockwise rotation. So shear is down in this case. How about the moment? Clockwise or counterclockwise? And why is it counterclockwise? Happy beam, that's right. Makes a positive moment. Okay? All right, so now we can do our force summations again. Sum of the forces in the x has to equal 0. We're going to say to the right is positive. So I have the normal is equal to 0. Not very exciting. Let's try sum of the forces in the y direction is equal to 0. Up is positive. What's that equation look like, Paul?
5 kilonewtons minus V.
So we find, look, what do you know? V is equal to 5 kilonewtons still. The last one we need to do then is sum of the moments. Where do we sum the moments about? The cut face, always. Okay. So this is going to look like if I'm summing the moments about the cut face, the only force that causes a moment in goes through it, V is on it, so it's just 5 kilonewtons times its distance, which looks like 5 meters, and it's going to be in the negative direction, plus the moment right here, our unknown, has to equal 0. So when we solve this equation, we find that the moment is equal to 25 kilonewton meters. That's interesting. It's going up. Okay. So it turns out that beams typically fail due to bending moment, not shear. Okay? So it's not the actual load causing the beam to break like that, shear off. It's that it bends it until it breaks. Okay? And we'll talk a lot about this in strength of materials. But this is how you see that the bending moment changes as we go from here. What do you think the bending moment is at A?
0.
Yeah. Goes from nothing here. In the middle here is where this particular beam is going to peak, and then goes back to 0 down here. Okay? All right. Let's try another one.
So in that
Yeah.
last question, so in this question, I guess, will 10 kilonewtons ever do anything
Ah.
for any of our
Great question.
calculations?
Would 10 kilonewtons ever do anything? Yes, it certainly would. It does two things. First, without the 10 kilonewtons, we wouldn't have the 5 kilonewton reaction to start with. Second, let's do D. Let me get some more paper out, and we'll do D. Okay. So let's do joint D. So free body diagram of joint D. What's it look like, Vlad? What else? Maybe 5 kilonewtons over here. Throw the 10 kilonewtons on here. Shear force going down. Bending moment going counterclockwise. Exactly. Okay. So now, when I do my force summation, right, X is still boring in this particular beam. Some of the forces in the Y, though, now I have 5 kilonewtons minus 10 kilonewtons minus V equals 0. V now equals what? Negative 5 kilonewtons. Okay. So before it was 5 kilonewtons until we hit this 10 kilonewton concentrated load, and then it flipped directions and is 5 the other way. Yeah.
But don't we, if we just do this from the other side, we get the V is pointed up now, and it'd be +5.
So let's finish this and then we'll do it from the other side. Okay. So now let's sum the moments about the cut. Set those equal to 0. Counterclockwise is positive. So summing the moments about the cut, I'm going to have 10 times 2.5 minus 5 times 7.5 plus M equals 0. So this is 25 minus 37.5. Looks to me like the moment is 12.5 kilonewton meters. Okay. You all right with that? So let's do the same point D, but instead of looking at the left-hand cut, let's look at the right-hand cut. So now my free body diagram looks like this. What do I do on this cut face? Anyone? Max? Where's the normal force going to go? This way? Yeah, Victoria? Okay. Where's my shear going to go? Up, because it causes clockwise rotation. And the moment, clockwise or counterclockwise? Clockwise. Happy beams, right? So now let's sum our forces. Always start with the X. So far in this beam it's been very boring. N equals 0. Move to some of the forces in the Y. We're going to say up is positive. So now I have 5 kilonewtons plus V equals 0. Oops, sorry, I'm off the page. Right? So it looks to me like V is negative 5 kilonewtons. So it matches what we found in the one before. So the shear has switched directions. Okay? And if we sum the moments about the cut, counterclockwise, as positive, I'll have negative M plus 5 kilonewtons times 2.5 equals 0, or M is equal to 12.5 kilonewton meters. Okay. All right.
So 10 didn't really matter because of the symmetry of the beam?
Well, so the question is, did the 10 didn't really matter because of the symmetry? No, it does. The 10 totally matters because it puts the reactions on the ends, right? So you have to include all of those loads. Yep. You're right, though, in saying, well, if I moved the 10 to a different spot, it would probably cause a different reaction. Absolutely. Okay? All right. Let's try another beam now. Okay, we have a 9-meter long beam, and that's 5 and 10 kilonewtons acting on it. And I want you to find for me the internal loads right at the middle. Okay, so I'll call this section AA. So we're going to cut it open, and we're going to figure out what those loads are. But before we do that, what do we need to do? Reactions. Right, Sierra. Always solve for the reactions to start with. Okay, so why don't I pause, and I'm going to let you solve for the reactions just so you get your practice at it. I know you can do it, but let's see it. Did you all get some equations like this?
Yeah, I thought that's at 11, not 10.
And let's see, we could solve for BY 15, and 60 is 75. 75 divided by 9 is going to be like 8.5. 8.3. Okay. Right. So then 8.3 comes up here. We'd have 1.7. 6.7 is AY. Right? Everybody good with that? Okay. So now, now that we know that, AY is 6.7, BY is 8.3, why don't you go ahead and section it and draw the free body diagram. Okay, and then we'll check back. Hopefully you get a free body diagram that looks something about like that, right? Next step's going to be to solve for those. So let's sum the forces in the x, say that's equal to 0. Looks like our normal is equal to 0. When is the normal not going to be equal to 0?
Cables.
Yeah, when there's a force with an x component, right? If there's something that's going along the axis, until then, the normal's pretty boring. Okay? Looks to me like the shear force is going to be 1.7 kilonewtons. Can't do that one in my head. What'd you get for the moment?
22.65.
Excuse me?
22.65.
22.65 kilonewton meters. Anybody else get that? Okay. Where do you think the maximum shear load is in this beam?
Just on the other side of the 10. Just on the
It's
right-hand
equal,
side.
wouldn't it? Because 8.3.
So you think it'd be just right here for the maximum shear force? No, that's
Oh, shear force?
yeah, maximum shear force.
Uh,
V, maximum V. Where's max V here?
I'm still gonna go with that spot.
What's that?
I'm still gonna go
You're still going to go with this spot? That's good. You're right. It's this spot, but it's also this one. And it's also that one.
Okay, so it's just right.
And it's also this one. Right? It's any place in here. Because think about it, if we did the free body diagram of this little slice, what would this shear force have to be for it to be in static equilibrium in the y direction? 8.3, right? What about if I move my thumb over a little bit? Still has to be 8.3. Agreed? Can go all the way up to here and it's going to be 8.3. Right?
But if that was a distributed load, then it would be different, right? Like
If it was a distributed load, it would change as I went across there. Indeed. Now, what about the moment? Where's the maximum moment in this? I'm going to tell you beams typically fail due to the bending moment. So we need to know where that is a maximum so that we can do some calculations. Where's the maximum bending moment in this? The middle, you think?
I think a little bit closer to the 10, yeah. Between A and 10, yeah.
Maybe someplace in here? Yeah, but we don't know exactly where, do we?
Figure it out.
We could. Maybe. Right? But right now we don't know exactly where that point is. But you can understand why that point's important. We could guess and check, right? We could keep slicing it and see, like, start at A, move over a little bit, see if it gets bigger, move over a little bit more, is it still bigger, right? And go closer and closer. Or we could make a plot of it, a chart, which that sounds nicer, right? Okay? That's what we're going to be doing on Wednesday, okay? We've got some more work to do just on these, though. Any questions on this guy? It's not, like, super scary, right? Method of sections probably has you well prepared for this. So let's do another new one. This time, I didn't give you a note packet because, well, We're drawing sticks. Okay. Let me get this out here so it's not distracting, hopefully.
Bless you.
Everyone got this in their notes? Okay, so go ahead and solve for the reactions. Okay, give you a minute to do that. All right, hopefully you got a system of equations similar to this one. If you did anyone get a value for by and ay? See, we'll have 3 times 5 is 15 times 2.5 is 37.5 minus 4 times 8, which is 32. So it would be at negative 69.5 divided by 10. So I think by would be 6.95 kip, and ay would be 15, and 4 is 19, so 19 minus 6.95, 12.05 kip. Yeah? Okay. And AX we found to be 3 kip. All right. Let's do a couple different spots on this one. Let's do point C, which I'm going to say is halfway through. And let's do point D, halfway through the distributed load. And let's do point D, which is halfway through the B. Okay? So let's draw a free body diagram at C. Some of the forces in the X. Haven't my summation signs got better this year? I'm telling you, over the summer I get really rusty and these get sloppy, but then the more I teach statics, the better they get. So it looks like I have 3 kip plus the normal equals 0. What's that tell us? The normal is -3 kip, meaning that it's compressive. Makes sense, right? If we look back at the drawing, the force vector is pushing it that way. If it's pinned here, it's squishing it, right? Okay. I'm going to add another place for us to look at too. I'm going to add E, which is just to the right of this force. Okay. So let's sum the forces now in the y direction. Up is positive. Looks like I'll have 12.05 minus 3 kip feet, 3 kip per foot, I guess, times the length of that, which I said it was in the middle, so times 2.5 feet, minus V equals 0. So 3 times 2.5 is 6, 7.5. So 12.5 minus 7.5, 4.55? V is equal to 4.55 kip. Sum of the moments about the cut has to equal 0, counterclockwise positive. Okay, so if I'm summing about the cut, I'll have M, my unknown. I'll have the moment due to the distributed load. That's also going to be positive. So the distributed load is the 3 kip per foot times 2.5 feet that it acts over. Right, so 7.5 kip. And it acts half of 2.5 away, so 1.25 feet is the distance. Right, so this is the force. This is the distance. Right? Because I'd have just one force acting here. If I simplified that distributed load, that'd be 3 times its length, which is 2.5. So I believe that's 7.5 kip. Okay. And it acts 1.25 from the cut. What else do I have causing a moment? 12.05, right? So minus 12.05 kip times 2.5 feet equals 0. Anybody solve for the moment? 20.75 kilonewton meters. Kip feet. Yeah. We just missed Mars, everybody. Okay. How you feeling about this? Pretty good? Better than Wednesday stuff? Yep. Well, if you practiced in between now and then, you know, yeah, well, I know. It's okay. I didn't grade papers till this morning, so. Let's go ahead and look at E as the last. Let's skip D and just go straight to E. Well, I don't know. So there's one free body diagram. That one looks more complicated, right, than if I just looked at the opposite one. Wouldn't you agree? So let's look at the right this time. Okay? So what would the forces at the cut face be if I look at the right-hand side? Normal, and which way does it go? Out of the face, right? Shear, up or down? Up, because it causes clockwise rotation of the member. Moment, clockwise or counterclockwise? Clockwise, why? Concave up or a happy beam, right? Okay? Now, this is a pretty simple force summation, but let's start with some of the forces in the x equals 0. To the right is positive, so I'm going to have negative normal equals 0. What's the normal force? 0. That's weird. Because over here, right, we said that it was 3 in here the whole time, negative 3. Why is it 0 over there? Why in the world do I get a 0 normal force to the right of E?
Because it's not being affected by that. Yeah, it hasn't been applied yet, that downward sloping force.
Okay, well, no, I'm to the right of it. Okay, so this downward sloping force acts at E, but this part that's to the right of that doesn't experience any normal load. Because A of X is holding it. Now, if I switched and I put my pin joint over here and my roller here, what would change?
The X, like
Everything
everything in the X.
in the X, but you can do it in your head. How would it be different if I moved the pin joint to over here and the roller, if I just switched them?
A sub X would be in tension.
Okay, so the normal would be in tension, and where would you have a tensile load in it? Between A and E or between E and B?
E and B.
Yeah, between E and B, right? And then there'd be no tensile between A and E. Because this is pushing it and it would be pulling against this joint. Okay? All right. Okay. So let's do some of the forces in the Y equals 0. Looks like I'll have shear plus 6.95 equals 0. So shear is going to be negative 6.95 kippers. And sum of the moments about the cut equals 0. Counterclockwise is still positive. But how I have this drawn, I'm going to have negative moment plus 6.95 times 2 equals 0. That's because this is 2. I'm always summing the moments about the cut here. So that eliminates the shear and the normal. I could sum the moments, right? I could sum them about this end, but then I have to account for my shear load there. And it's just more direct to do it this way. Okay, so it looks like the moment is going to be 13.9 kip feet. Kipper feet. Okay? All right. Let's give you one to work on at your table. I'm seriously not going to help you.
Very nice. You trust us. He trusts us.
Let's see what you did there.
I got one. And no, I'm gonna go buy some after this, but I've gone through a ridiculous amount of engineering paper this term. It must be, yeah, it's crazy.
Yeah, it's kind of like that's what I think you just said.
Engineering.
What is that, 5?
Kilonewtons per meter. You got this? Okay? So it's a triangular load. You need to solve for the reactions, and cut it at C, and solve for the unknown internal loads. All right? Give me about 10 minutes to work on this. Here's my free body diagram so far. I highly recommend looking at the right side of this instead of the left side. If you looked at the left side, what would you have to do? Excuse me? Rectangle and triangle. Not just, you couldn't just include the resultant, right? Because it's, when you drew that free body diagram, you'd have a trapezoid, right? Whereas if you draw this free body diagram, you just have the triangle, okay? So common misstep here, right, is if I cut it here, to still put the whole load of 30 kilonewtons on it right here. Well, there's not a whole 30 kilonewtons acting there anymore, okay? So you gotta, if you cut it here, you'd have to refigure out what that load is by using the kind of trapezoid thing. If I do it on the right, I can do it this way. Okay? So I'll give you a few more minutes with this in mind to solve. So these are the numbers I got. So nothing in the horizontal, so your normal is going to be 0. In the y direction, you're going to have shear, negative 15 kilonewtons, positive 10. So I get that the shear is a positive 5 kilonewtons. When I sum my moments about the cut, the moment as I have it drawn there is negative, right? It'd be positive moment, bending moment on the beam, but it's negative when I choose my sign convention of counterclockwise being positive. So negative moment minus 15 times 2, because 2.5 times 6 is 15, I think. Yep. And then 2 is, it's 1/3 from the fat end, 2/3 from the skinny end, right? So 15 times 2 plus then 6 times 10, because I have 2 and 4 is 6. 6 times 10 is the moment of the BY reaction. And so I get negative 30 plus 60 is a positive 30. Take m to the other side, and I end up with m equals 30 kilonewton meters. All right? I think we're reaching the point of mental fatigue at the moment. You guys have been doing really good today. Followed along all the way. I'm going to leave you here. This is section 7.1. I want you, after you do your 3 machine problems, to do 3 of these problems, or as many as it takes that you start getting the right answers 3 times in a row. Okay? If you can get the right answer 3 times in a row, you're probably set. Okay? Exam will be a week from Monday. We have no class this Monday. Graded problem will be due on Wednesday, and I will post it within an hour or 2. All right? Thank you. Have a good weekend. So, funny thing, I did this wrong because I forgot to do divided by half here, right? So it's 2.5 times 6, which is 15, but since it's a triangle, I need to divide by half. So that's going to be 7.5. So this right here would be 7.5, which would make this, let's see, 2.5 or negative? Yeah, it's going to be negative 2.5. And then that would make this, 7.5 times 2 is 15, and then 60, so it's going to be 45 kilonewton meters. Sorry, everybody.
Thank you for the correction.
Yeah. Now you can have a good